Alright, we're recording now. Okay guys, so we'll get started now. So what we're looking at in this lesson is we're talking about writing a plan for the lab report. Okay, so I know you've already had a little bit of time on what you're doing with the lab report, so you all know what experiment you're doing, right? What's it called? Yeah, no, don't all say it at once now. Which one is it? Bradford, isn't it? Yeah. So what we're going to be talking about now is just the plan for this experiment. Now, maybe just before we get started, can anyone think of any differences between, what you might have in the plan for the experiment versus the lab report? What might be something different between the two? Yeah? Say again? Yes, it's very difficult to have the results in the plan, isn't it? So that's a good example. What else? The language. Now, how is the language different, the grammar? Yeah? Is which? And the plan? Yeah, so, okay, give me an example of a sentence in the plan then, like of the tense. Yes, that's it. Good. Okay. Incubate the whatever. Good. Okay. And then in the lab report? The thing was... Okay, good. Good. So what we'll do is I'm going to just write on the board the structure of the plan. I'd like you to copy these bullet points down. Now, not every single section... Diego, what's wrong? No, not every single section you may need. So the list I'm going to give you would be like a maximum list, okay? But there'll be a couple of things that maybe you could delete depending on the situation. But we'll talk about that in a moment. So if you can just make notes, some key sections you might need in your plan. Date. Okay, now let me explain the first one here. Problem statement. Now, date problem statement. This is really more relevant perhaps for the physics lab report. Maybe not so much for what you might be doing. So this could be nearly an optional section. The problem statement is the problem that you are given from the teacher. So for example, if it was a physics lab report, the problem statement might be something like, describe an experiment to calculate the value of G using the equipment available in the lab, or something like this. It's kind of like your problem your mission you've been presented with. I don't really think this section is appropriate for your lab report, but, in some situations in the future, you might find it necessary to put this in. You had some problem to solve and some limited resources and it was presented to you from the teacher. So, you can make note of this, but I'll just put a little X here because I don't really think you would need it necessarily for the Bradford one, okay? The next one, which I believe you had a talk about already, is the hypothesis. Now, you were talking about this already, right? And even if you weren't, you're all science students, so I'm sure you know this word hypothesis, yeah? So what would be a simple description of hypothesis? What exactly is it? What is it, Zach? Yeah? Yeah, okay. Yes, okay, yeah. Something else, maybe? Assumption, something you want to test. Yeah. An educated guess, perhaps you've observed something and you want to test your prediction, your claim for it, yeah. So, you've done the language for hypothesis? Or not? You've done the language for hypothesis. So in a little bit we'll practice writing a hypothesis for Bradford anyways, but you all know it, that's good, okay. So anyways, obviously you'll need this section. Okay, next now is aim. Have you talked about aim, or is this a concept you've seen? It is? Object, yeah, okay, so I don't know, Lorraine, do you want to make a big distinction between aim and objective? I don't think so. Yeah.
I use the word the aim of.
Yeah, yeah. If we're going to be picky with language, aim and objective are different, have different meanings, but really not until you're at sort of master's level where you're doing research that you have to be really careful with your choice of language here, okay? So we'll use aim here. It's not quite the same thing as objective, but at this level, nobody's going to make a big deal getting the two mixed up, okay? I think this is more of a concern for the master student. So aim, anyways. Next section, we'll need apparatus and materials. So obviously this speaks for itself. It's the list of equipment and materials you had available to you. Now you've talked a little bit about Bradford, so you probably have an image in your mind of some of the things you might need for the Bradford experiment. What might be some equipment that would be needed? Yeah? Spectrometer? Yeah, what else? Thermometer, yes, okay. What else? The test tubes? Yeah, yeah, what else? Yes, all this type of stuff. Oh, good, okay, so you have a list there, the equipment you would need. Next, now, I don't know if you've talked about what variables are involved. So have you any idea of what variables are involved in the Bradford? Yeah, well that's just the two different types, but what things are you measuring? Yeah? Yes, okay, that's a variable. Yes, that's a variable, yeah, what else? I think volume as well, isn't it? You know, how much of each substance you have and all this, yeah? That's probably a variable too that you might want to know. Okay. Expected results. Now, this doesn't mean you make a prediction and a guess of the numbers from doing the experiment, okay? The expected results is just really, like the name suggests, what you think is going to happen or what you expect to happen. So with the Bradford, your expectation is when you make the graph at the end, it should be what shape? Or maybe you didn't talk about this yet. No?
If something is proportional.
Yeah, have you mentioned proportional? What type of graph does physics students, surely? What type of graph does proportional make? Linear, okay, yeah. So you're expecting when you plot your variables to get a linear graph, and the linear graph, so to speak, verifies the proportional relationship. Yeah, so this is what you would expect. You would have a problem if you didn't get a linear graph, if you were claiming that it was proportional, right? Okay. Treatment of results. So, one problem with the Bradford experiment, I mean, you'll see it when you're working on it later, is that in some situations you get a value which is outside the scale that you're operating with. You know, you get a number too big that you shouldn't really be using it. So an example might be, you know, maybe you have a weighing scales and it has a max weight of, let's say, 100 kilograms. And most of your readings are measuring 20, 21, 22 and so on. But maybe you start making readings of 99, 100, 101. Well, we've got a big problem, especially if we're having numbers like 101, right? Because the weighing scales is only rated to go up to 100. So should you really be using that value of 101? Should you? What do you think? No, you shouldn't. Why not? It's outside the measuring equipment's range. And that's something that happens with the Bradford experiment, that you get one value that's just outside the range. You shouldn't really be using it, and you'll have to think of a way to get it back into the range, you know. So for example, with the weighing scales, let's say we're measuring, I don't know, a bag of potatoes, and it's 100 kilograms, or 101 kilograms, but we're not quite sure if that's accurate because we're outside the range. Well, what's one thing you could do to get an accurate reading of, a better reading of the bag of potatoes? Yeah, that's it. Yeah, weigh half of it and then weigh the other half. You know? So you've now brought the measurement within the range. Okay? So that all falls in the category of treatment of results. So for the Bradford, when you're researching it, you'll have to write something about how you will treat the results. You know? Another thing we'll have to do with Bradford is that there's a systematic error with all the measurements. So all the measurements are off by a certain value of A. We'll have to bring them all down, calibrate it, so to speak. This will come up too. Okay. Yeah. Okay, and the last thing, the last nice section, sources of errors, or in other words, or other potential problems, assumptions. So with every experiment, you're going to have to make some assumptions in order to do the experiment. And also, with every experiment, you're going to have some sources of error. Now, maybe you've talked about sources of... Have you talked about different types of error? Maybe not. No, yeah, it's a little bit too early for that. There'll be another lesson later where we talk more about uncertainty and errors. But some you might already know from perhaps high school. What are different... Systematic error, which I just mentioned, yeah. What type of error is that exactly? With the apparatus, yeah. There's perhaps an error with each measurement, but it's the same error. Yeah, like this one, yeah, that's another type, yeah. Any other types?
Human error.
Human error, absolutely, yeah. You turn the machine on the wrong way or something. Yeah, so these are all sources of errors, yeah. Now, what I'll do now, I want to give you some key points of what I want to see in a plan, okay? So these are just the main sections, but a key things to see, with, in particular, let's see. Oh, well, let me see. I left out, well, actually, maybe you can tell me. I left out a rather important section. I skipped over it. Anyone see a rather critical section missing? The blooming experiment and what you do. Yeah, so we'll stick it in here. We'll just call it method. Now, how is method different to what you write in the lab report? The tense, obviously, yeah, but something a bit other than the grammar. What's a key difference between the... Which is which? Good, yeah. For me, I like the plan to be bullet point. But in the lab report? In paragraph, yeah. And what's another difference between the two? So, let me just put this here. Here I want it in point form. What's another difference? Which will be bigger? Yeah, why? Full sentences, yeah, okay. Something else perhaps? Do you want me? Okay. Why would the lab report be bigger? Okay, let me put it like this. If you do everything in the method in the lab, then it'll be the same size, you know. But you might discover when you're doing the lab report, oh, there's something else, something you have to do differently, you know. Or maybe there's a problem. You might not discover this until you're actually doing the experiment, you know. So the lab report will always be bigger than the method because it's real life where you actually do it and perhaps you discover problems that need to be corrected as you're doing it. Yeah? Okay. So anyways, a couple of points. Do you all have those sections? Yeah? Okay. Are you heading off? Okay, very much. Right, so I just want to expand a little bit on the, well, okay. Obviously the really important section here, they're all obviously important for different reasons, but the method is rather important because this is what you're physically going to do and you're really supposed to stick to it. You're not really supposed to be changing it or worse filling it in later after you do the experiment. You should really try to stick to it. So what do we need to see in the method? So I definitely want to see how to measure all the quantities. So when you write your plan, you need to demonstrate to whoever's correcting it that you know how to measure your quantities properly, you know. So I'm trying to think of an example maybe that you'd be familiar with. Let's say you were measuring the temperature of something. Would it be a good idea to leave it on the table for a few minutes before you measure the temperature? Well, maybe not. Maybe you need the temperature straight away before it cools down. You know, so these you need to convey to the marker that you understand this. So when you write your instruction, you would need to include something like measure the temperature immediately after whatever it is that you've done. You understand? You need to sort of show whoever's marking your work that I understand a potential problem here and I've made sure that that's not going to happen. Yeah, so how to measure all the quantities. Another thing which might be difficult to do is to justify choice of equipment and instruments. Now, there might not be a lot that you can say about this because often you have very little choice in what equipment you use. But sometimes you do have good reasons for the equipment that you're using. That's very, very important. Like why would you use a pipette and not, you know, just pour it into a test tube and read it off? Like what? Yeah, pipette is more accurate, isn't it? So you need to justify this in your plan. If you made a choice to use a pipette, you need to say why. You know, so like something along the lines of using a pipette for more accurate readings. You know, just some justification for why that particular piece of equipment was used. Yeah. Now you don't always have a choice. Like I think you know, if you have to use a spectrometer or whatever, you have to use it. You know, to measure the values. It's not like you have I don't really think there are many different equipments that you could use for something like this. Okay. Now, this one, you have to demonstrate knowledge in your method of correct measuring techniques. So, by this, it's kind of like good measuring practice. So what would be a good measuring practice? Any ideas? No? Very good. Repeat. And take an average. Excellent, yeah. So I think for the Bradford experiment, everything is done in triplicate. You do all your readings 3 times and take the average. This is a good measuring technique. Bad measuring technique is just doing it once. Yeah? And also, perhaps you could say a bad technique would be doing it too many times. You know, especially if time is important for the experiment. If too much time passes, maybe that contaminates the results. So 3 seems to be a good number. Now, control other relevant quantities. So these are other variables in your experiment that might interfere. Okay, so if you're doing an experiment where temperature is very important, then you absolutely want to make sure the lab is staying at the same temperature if possible, right? What about in Bradford? Can you think of anything important to control for? Yeah.
What's the word? Control other.
Control other. Sorry, relevant quantities. What other things what things can we control for in Bradford? Yeah, because you buy them, they come in packs, don't they? Already labelled. Yeah. What else? Yeah, you want to keep the lab temperature constant because Obviously I don't have a biology background, but I would imagine that the temperature in the lab might affect what's happening in the test tube, right? Yes, okay, all right. You all seem quite insistent on that. Okay, next. Oh yes, so I think I heard a couple of you mention this earlier. You need to state what are the independent and dependent variables. So which is which? Which is the one that you change? You can. Which one? Yeah, and the one that you then observe the change in, dependent. Yeah. Yeah. So that's okay. You need to say what's that? Okay, just a couple of more things here. You obviously need to have a labeled diagram. I think that goes without saying. And you also need to talk about safety. So again, what are safe lab practices? You know, what's a potential danger in Bradford? I don't know. Is it dangerous to drink the concentrations? I don't know. Is it? No? Maybe? Okay. Maybe not do this. Anything else? Yeah. Yeah. Lab coats, all this type of stuff, right? Yeah. Yes. Okay. How the data is collected, and then how it'll be used. So I think for the Bradford, there's certain values on the test tubes already, like the concentration and so forth, I believe. And also the machine outputs the value of A. So the collection here is quite simple, really. You know, for some other experiments it might be a bit difficult, right? You might have to measure the temperature with a thermometer, you might have to weigh something. But for the Bradford, the collection part is actually pretty easy. You're really just reading it off a machine. It's pretty straightforward. Okay, yes? So what I'll do is I'll show you the video. Now, what I was kind of hoping for today, but I don't really think the time will allow it, is after you watch the video, we maybe have a look at what people are writing and talk a little bit more about it. But I think what we'll do is we'll watch the video, and then I'll leave this as a homework for you to get started on, to try and put together a plan. We'll see where people are, what people have produced, and then we'll talk about maybe refining this a bit more. Yeah? Is everybody clear enough on the basic kind of structure for it? Yeah? Okay. We'll put the video on now. I think the sound should be okay. It's not that long of a video, but what's it, 10 minutes was it? Less than that? Yeah, okay, okay. I think what I'd like you to do is to make some notes as you watch the video. What would be really fantastic is, as you're watching the video, you can make some notes of things you might think would be good to put in your plan. You know, maybe you might see him mention something about safety, maybe you might see a particular measuring technique, maybe you might see a potential cause of an error. Yeah? Okay, any questions before we start? No. Well, watch the video and I'd like you to make some notes. I'll leave it as a homework to get started. Maybe we'll pick it up next week, or if not, we can do it in another hour, maybe in a tutorial or something like that. We'll see how you get on. Is this the first thing you're starting to write in their academic skills, isn't it? Yeah, okay, so it won't stress you too much then, I hope. You all have pen and paper? Yeah? Oh, I should say, in real life, of course, you make the plan. Let me stop this side. In real life, of course, you make the plan and then you carry it out. You know, we're kind of cheating here a little bit by looking at someone do it, and then you're pretending you're coming up with your own plan. Okay, but I don't expect any original thought at this level. That's further level, okay? So we'll watch the plan and we'll imagine we're designing the experiment afterwards. Yeah? Now, this is not working. Good. So I guess he took this on his phone, huh? Yeah. Wait. I need. How do I pop the volume up a bit more? Shapers. All right. Well, maybe.
Today's practical involves the determination.
Is that the loudest can be on the thing?
It is. It's up all the way. Is this not loud enough?
And how about on the thing behind you, the model paper?
This?
Yeah.
Oh, yeah. Okay. That might be too much now.
Target cells,
Oh no. Okay.
you need light.
All right. Are you all ready? Yeah. Yes. What's wrong?
It sounds like Nikita.
Sounds like what?
Nikita.
So good.
Right. Okay.
Today's practical involves the determination of protein concentration in a sample cell lysate. For this practical, you will need your sample cell lysate. In this case, it comes from Jurkat cells. You will need lysis buffer, bovine serum albumin standard, and Bradford reagent. In addition, you will need pipettes, pipette tips, and a 96 well plate. On your protocol, you will notice that there is a table constructed that will show the final BSA standard concentration. These are a series of standard BSA concentrations ranging from 0 micrograms per mil to 1000 micrograms per mil. The required amount of BSA is indicated on the middle column along with the required volumes of Bradford reagent and lysis buffer. All of these should be mixed thoroughly, and the protein concentration per well should be indicated by filling in the table. The first part of the protocol involves preparation of the standard curve. Please carefully read the exact amounts that are needed to be put in each of the wells indicated on the left-hand column. All of these additions are performed in triplicate. Start by adding in the lysis buffer, then the BSA concentrate, the appropriate BSA amount, and then the Bradford reagent. The first part involves adding in the lysis buffer. Please make sure you have your pipette set to the correct amount, in this case 200 microliters, and carefully pipette in the exact amount of lysis buffer. You then need to change the volume on the pipette for each of the appropriate amounts of lysis buffer. The next one being 175 microliters. Once you've added in all of your lysis buffer, you would then have to add in the BSA. The BSA is a known standard and has a given concentration, so the amounts are indicated on the table and will need to vary for each of the different wells. The first amount is 0, so you don't need to add in any BSA into the first set of triplicates. For the second well, you're required to add 10 microliters. So 10 microliters is pipetted into row number 2, well A to C. This is then increased to 25 microliters for the third set, 50 microliters for the fourth, 75 microliters for the fifth, and 100 microliters for the sixth. The Bradford reagent that you used is kept in the fridge in a stock bottle. This will, however, be aliquoted for you and allowed to come to room temperature for at least 30 minutes before use and aliquoted into an appropriate tube. You will need to add in 200 microliters of Bradford reagent to not only your standards but also to your sample also. Once your standards have all been added and mixed, you should then start adding your samples again in triplicate. So for each of your lysates that you've been given, you should add the required volume to the microtiter plate and mix it with lysis buffer and Bradford reagent like you did with the standards. Carefully add your lysate to the appropriate wells. You should do this in triplicate. You should then add the required volume of lysis buffer. Again in triplicate. And finally, you should add the required volume of Bradford reagent. Once you've added the required volumes for both the standards and your sample lysates, it should be allowed to incubate for at least 30 minutes to 1 hour at room temperature. This then will allow the colour to develop between Bradford reagent and the protein that's present in your samples. The last part in this process is to read the absorbance using the spectrophotometer like before, but this time at 595 nanometers. Once you've taken your absorbance readings and gathered your printout, you should plot the absorbance versus concentration and generate a standard curve, both in your graph paper and in your lab copy and also in graph algorithm. By reading the absorbances of the unknown, you should now be able to get an average and extrapolate the concentration of the unknown protein lysate.
Determining protein concentration. For this lab,
Okay. Did
No.
you get the extra sheet?
Oh, yes, we'll give that to him now. So does this need instructions, Colin? Or
No,
there-
that just goes with it.
that just goes with it, okay. They could they have access to the video?
Absolutely, yes.
Yeah.
I'll send it out.
So Colin will send
Yeah.
on the video link. You
So-
might have to watch it more than once. But you probably noticed a couple of things in it already, like notice the Bradford reagent had to be in the fridge and then bring it out to room temperature for how long? 30 minutes, yeah. There was another temperature thing in it as well, wasn't there? Oh yeah, the incubation. Well, how long did you say for that one? An hour, was it? 30 minutes, an hour, yeah.
I'm just going to leave whatever they need on here. Just stuck it down in the end. No, it's just empty boxes where you can fill in. Because I thought they were going to be typing in glass, so I just haven't they might not need to use what he just did. He's got that on him. He's puts that on. I'm not hearing it. He's got it on his machine.